Hello and welcome back to Let's Code Physics. I am very excited to get back to our toy chemistry code today. I've had a little bit of delay in working with this code due to Hurricane Irma, but everybody and everything is fine, including my laptop here. And so I'm excited to get back into this today. I've made a few changes since the most recent video. You might recall last time I was a little bit concerned about how the bonding and unbonding rates were identical. So the rates of forming and breaking bonds were identical, and that didn't sit right with me because it seemed like once you formed a bond, it should be more likely that you keep the bond than it is that you lose the bond. And so I went back to the original paper and found this wonderful clause here that first of all, this R value that we calculate is the bonding and unbonding rate. So this gives you both the rate of bonds forming and the rate of bonds breaking. So I was very happy to see that I hadn't missed another equation somewhere. I just missed basically this line here in the paper. And so I was correct to use this setup for both of them. But what I also missed was that I was using this EIJ as a factor in this EAIJ for both of them, because up here you've got that EAIJ equals the barrier, which we have correctly, minus EIJ, and I was using this version for EIJ for whether they had a bond or not, except that I missed the context here. You always got to read the sentence around the equation. They either share a single bond of internal energy, EIJ, so this is the bonded energy, or they do not, in which case EIJ equals 0. So when they have a bond, we're supposed to put in this factor, and when they don't have a bond, we're supposed to set that factor equal to 0. And that's what produces in this graph this difference between these two wells. So here they are unbonded, they're just experiencing the external potential. Here's the bonding and unbonding barrier, and here we've got the bonded state, and so they're in a lower state. And I kept looking at this thinking, those are different, so it should be a different amount of energy to get over the hill this way than it is to get over the hill this way. I just didn't know how to put in that difference. It turns out this one thing here is the difference. So if we go back over to our code, I'll show you where I've put that in here. All the way at the top, we defined EA and EB before. So this is the transition barrier for forming a bond. This is the transition barrier for breaking a bond. And so all I had to change was this one line, that for an unbonded pair, E12 is 0. And for a bonded pair, E12 is this value. Oops, that needs to have the minus epsilon value. I had tried removing the epsilon from here, but that took it in the wrong direction. So I have this correct now. So this is this is no bonding energy, and this is now the bonding energy, right? Because if I'm going to form a bond, I need to have no bond initially. If I'm going to break a bond, I need to have a bond initially, right? So I believe that's what I've got here, 1/2 K delta x squared minus epsilon, 1/2 K delta x squared minus epsilon. And that, of course, is getting subtracted here for this EA that goes into the exponential over here. So that means that you are more likely to go from unbonded to bonded than you are to go from bonded to unbonded. And now that finally makes rational sense. But I wanted to check to make sure that that was working out, right? So it's nice to be able to say that I've put it into the code correctly, but what I'd really like to do would be able to see that I've got bonding favored over unbonding. And so the way I've set that up, I've set up a little check for that. If I scroll down here, I've set up a new variable called bonded. Or excuse me, time bonded. The bonded is going to be the graph, so we'll worry about that in a second. But what I've set up is this thing, time bonded, and this is the amount of time that particle 0, that's the driven particle, has spent with one or more bonds. So if I've set this up correctly, if I've set it up correctly to where I'm matching that potential energy diagram from the paper, then I should expect any of the particles to spend more time bonded than they do unbonded. So I should expect this to exceed 50% of the total time. So we start that out at 0. When we go into the loop, here's our extended Euler-Kromer code with all of the force calculations. What I do after I evaluate the time, or after I update the time, excuse me, I check for whether particle 0 is bonded. So that's kept track of in the bonds matrix. So we check elements 0, 1 and 0, 2 to check whether particle 0 is bonded with particle 1 or whether particle 0 is bonded with particle 2. Of course, I'm not going to check 0, 0 because that would be particle 0 bonded with itself, which it's not going to do. And if that's the case, then I say, okay, so particle 0 spent some time bonded, so it spent this time step bonded, so we're going to add dt to this amount of time. And what I do down here is I just update the graph to say, give me the time as the independent variable, and for the dependent variable, give me the time bonded as a percentage of the total time. So if I have this set up correctly, and such that bond formation is favored over bond breaking, then we should expect this graph to, for the most part, exceed 50%. And that's what I have been seeing. Let's check it out now together. So here's our animation. You can kind of visually see that there's more bonds on the screen than there are non-bonds or black space. Let's go down here. Here I've got the driven particles percent time bonded, and you can see it's definitely above 50%. It only dipped below 75%, it looks like, at this one frame. And then it is climbing up pretty steadily. So here it's kind of random, but here it's climbing up pretty steadily, and I'm not sure, I mean, it has a level out at or before 100, but because we're in sort of the steady state now, these particles are closer together, and when they're closer together, they're more likely to bond because they've got, they're sort of deeper in that well. And so the steady state we expect is for more bonds to form, and that's exactly what we see. So I was very happy to get that fixed. I did add one other little housekeeping item that I'll show you since we have a little bit of time. I need to check to make sure that my dt, my time step, is reasonable. So I've added in this line here at line 72 to compare the time step with the driving period. So remember, our particle 0 is experiencing a driving force with an angular frequency of omega d. You can change that into the period of this force by taking 2 pi over omega d. And basically we want to make sure that that is large compared with dt. So the way I've set up this condition here is that we want to get at least 10 time steps for every time the driving force cycles through. You don't want to have dt comparable to the driving frequency, or it's essentially constant. You definitely don't want it to be larger than the driving frequency, or else you're picking out points along that sinusoidal function kind of randomly. And so if we ever change omega d or dt to break this the safety mechanism, it'll print a single warning that the time step may be too large. So then we need to either decrease the time step or increase the driving period, meaning decrease the driving frequency. So that's pretty cool. I'm happy with that. We're moving in the right direction with this. This was a pretty significant change. Now we've got this thing matching with the model in the paper we've been reviewing. So I think what we'll start doing next time is playing around a little bit more with these values and seeing what kinds of different outputs we can get. And then eventually I'd like to move this thing into 2 dimensions instead of just 1 dimension. So thank you so much for watching. I will see you next time. Bye-bye.